Hello everybody, hi AP Stats kiddos. We are talking about the nitty-gritty of the two other types of chi-square testing that we can do. So we've already completely covered goodness of fit. Now goodness of fit is used for a one-way table for the distribution of a categorical variable. Now today we're going to be talking about testing for homogeneity and then also for association/independence. We will interchange those words. Now, testing for homogeneity is when we have a two-way table for the distribution of categorical variable over several treatments or populations. So that's the difference. All right, so you should be filling in these missing blanks on your skeleton notes on your sheet that you received yesterday. So there are three different types of tests for chi-square. We've already done goodness of fit, right? Used for a one-way table. We just said that. Now, homogeneity, like I said, it's for a two-way table. Now, and this is for categorical variable over several treatments or populations. So think about a randomized experiment. You know, did the treatment make a difference? That might be when we use homogeneity. And the other option is testing for association or independence. Still a two-way table, but now we have a single sample of individuals from a single population is classified according to two variables. So we want to know if there's a relationship or an association, if you would say, between two categorical variables. When it comes to doing a chi-square test, if you're in the plan part and you say, I'm going to use a chi-square test of blank, and you forget which one to use, I'd rather you just say chi-square test than saying it's for homogeneity when you really mean association. Or you say goodness of fit when you really mean independence. So something to keep in mind. All right, talking more about testing for homogeneity. We've already kind of looked at an example like this in our class work we did yesterday and in the video that you finished up earlier. Talking about the St. John's wort versus the Zoloft versus the placebo. These were the hypotheses that we talked about. There was no difference in the distribution of insert context here. And then the alternative is that there is a difference. Now, when we did our expected counts, I didn't quite give you this cute little formula, but this is how essentially you would do it every single time. You would take your row total times your column total, and then divide it by the grand total of the whole table. So if you're not sure what that means, look back at your St. John's wort example for depression and see how that makes sense for each of our expected counts that we calculated. Now, how we do this in the calculator. This is a good bit of calculator work, especially for the do part of the calculation. Now, you can't do this for goodness of fit. Most calculators that are newer have a goodness of fit test. Sorry for those of y'all that you have an older calculator. But this one should be on all of your calculators. We already did this in our example, but just as a reminder, here's how we get to where we need to go. Enter your observed values into matrix A, your expected values into matrix B, find the right test, and then calculate. This will give you three different things. It gives you your chi-square statistic, it gives you your degrees of freedom, and it also gives you your p-value. Now you want to make sure if you're doing a full-on four-step process here for chi-square testing that you record, meaning write down your expected counts, because when we're trying to figure out if the large sample size condition is met, right, all of my expected counts are at least 5, you need to write down what they are. You don't need to show the work for how you found them, but you do need to write them down. And then also in the do step, always write down at least 1 or 2 terms of your calculation before just saying ... and then here's what the calculator told me. Now, testing for association or independence. The null hypothesis. We're saying there is no association between the two categorical variables in the population of interest. Another way you can word that, you could say that the two categorical variables are independent in the population of interest. Obviously, you would put context behind all these. Then our alternative would be that there is an association versus they're also not independent. The way you calculate your expected counts is the exact same way as you do for homogeneity. So when you're doing the do part for this, you can still use that chi-square test in your calculator. The only difference is your hypotheses and then therefore your conclusions. So if you're like, how the heck am I going to determine the difference between these two? They seem really similar. They do seem really similar, right? They're both for two-way tables. You calculate the expected counts the exact same way, but it's the hypotheses that are different. And it's who you're comparing. So for homogeneity, you're comparing the distribution of one categorical variable in two or more populations or groups. So one variable, two or more groups. Now association or independence, we're doing the relationship between two variables in just one population. Okay, so some things to think about there. That's going to be the big way that you tell the difference between the two. And we'll do some examples so you see. So, our first example is going to be, is your index finger longer than your ring finger? Does this depend on your gender? A random sample of 460 high school students in the U.S. was selected and asked to record if their pointer finger was longer than, shorter than, or the same length as their ring finger on their left hand. The gender of each student was also reported. The data are summarized in the table below. Now this is nice because it kind of gives us a hint in the question about which test we want to use. It says, do the data provide convincing evidence at the significance level of 0.05 of an association between gender and relative finger length for high school students in the U.S. So this is a call for association. Why does that make sense? Between two categorical variables in one population. So we took one population. We're talking about one population of high school students in the U.S. And we're looking at two variables, gender versus length of their finger. Okay? So let me switch gears for a second so we can see how this works. I changed my screen size, so I don't know if it's going to fit. It's not going to fit. Alright, I think I'm going to cut this video here and then go to a new one so we can see this one better. Actually, never mind. It turns out that I can change the size of the screen if I pause. The more you know. Okay, so let's go through and do a full-on 4-step process. So, first step, state. Talk about your significance level, state your hypotheses. So, what are we going to say? So we want to perform a test of the following hypotheses using an alpha of equal to 0.05. And I'm going to pause a little bit through here just so I can write, and then if you need to pause it, you can copy it. We want to perform a test of the following hypotheses at alpha is equal to 0.05. So we need to state our null. I love doing chi-square tests because there's no parameters to define like there were when you were doing other significance tests for means or proportions. So our null is going to be that there is no association between gender and relative finger length in the population of high school students in the U.S. There is no association, underlining for my own emphasis, between gender and relative finger length in the population of high school students in the U.S. So, like we were saying, it's one population, high school students in the U.S., and it's two categorical variables, gender and relative finger length. Okay. So we could have said these differently using the word independence, but since it said it so nicely here, I figured we might as well just use that. So then our alternative hypothesis would be the opposite. There is an association between gender and relative finger length in the population. Okay. we have stated. Now we need to come up with our plan, say what kind of test we're going to use, and check our 3 conditions. Okay, so let's go over here. What are we going to use? If our conditions are met, we are going to use a chi-square test for independence. You could also say for association, and it would mean the same thing. If conditions are met, we'll use a chi-square test for independence. And now we need to check our 3 conditions. First condition we always check is that it was a random sample, and it did say in the problem that it was a random sample of 460 high school students. So we have our random sample. Next we check our large sample size. So here's the point where we have to find all of our expected counts. Okay, and we need to make sure they are all at least 5. It's easiest probably for you to make a little table here, kind of mimicking the one up in the problem, but instead of filling it with our observed counts, right, because that's what these are. These are our observed counts. Make your own table using your expected. So remember, the new way we calculate expected counts, row total times the column total divided by the grand total. Okay, so let's see if I can zoom this out a little bit so I can see everything at the same time. Okay, so I'm going to make myself a little table here, just to the side, just so I have some space. I have female versus male. It's going to be very beautiful. And I've got my 3 different categories. I've got my index, which is longer. I've got the same, and I've got the ring, which is longer. And I'm just going to use this as just a way to organize. So, let's find my calculator. To calculate for our first one, okay, I'm going to do index finger total, which was 158, times the female total, which was 227, divide that by my grand total, which is 460. Oops, don't need that. And then I calculate an expected count of 77.97. So go ahead and figure out the rest of those. So now we have all of our expected counts, and we can clearly see that they are all at least 5. So I can say that all expected counts are greater than or equal to 5. So if you wanted to write expected over here, just so you know that that's what that is. Zoom back in. We still have to test for independent. We do need to check our 10% condition because this was not an experiment. So I believe it's going to be safe to assume that 460 is less than 10% of all high school students in the U.S. Okay, so I think I'm going to leave this here, and I want you to finish this example on your own, okay? And then, so all that's left to do is do, and then come into your conclusion. After that, I want you to do this next example, example 2, okay? So that's kind of your homework for today. Enjoy!